Hello, everyone. Welcome to ITS 520. So I'm just letting everyone in right now. Okay. So, all right. So I'm currently sharing. The Brightspace. Okay. I'm also going to go to the calendar here. Just really quickly. So let me share this. Right, so you should be seeing the calendar. So I want to just remind you where we are in this semester, just to kind of give you, some details. So we are really almost at the end. We're getting very close. So this is what we have left. So you can see here, last week we were covering a lot of little things about TensorFlow. Today we're covering just one thing, which is Keras. And then you can see next week, which is Thanksgiving week, on Monday, we will cover reinforcement learning. I'll go over that. And then finally, the last topic of the course will be on supervised learning, where I'll talk a little bit about singular value decomposition, which is it's like principal component analysis or data compression, basically. So those are really the last three topics on supervised learning this week. Reinforcement learning, and today we're going to cover Keras. Obviously, for those of you that take 530, we would basically pick up here, right? So we would pick up here in TensorFlow 2 in particular, and we would start looking at all the different algorithms, in the low-level API. But what now with TensorFlow 2, Keras is a little bit more in there, so I'll cover a little bit more of it then. But I think today we will be able to finish Keras, and you will have enough that you will have that additional tool, right? So if you remember the last homework assignment that you did, and by the way, I'm hoping to have your Twitter exams graded this week, so hopefully I'm shooting for that. I've been super busy with some papers, but I should have that graded this week, hopefully by Wednesday. But as I was saying, if you remember the last homework assignment before the Twitter problem, so one thing I'll ask you guys, don't keep sending me, if you've submitted a homework assignment, you should submit homework assignments via Brightspace. But if you submit a homework assignment via email, as I said, for whatever reason, you may have that option. Please don't keep sending it to me and asking me to confirm or just send it, right? But, don't expect that I'm going to confirm, okay? So because my inbox with this online is just exploding, and it's very difficult for me to go through all the emails. So please, I'm going to ask you to do me that favor. Submit it. I'll get to it. I promise. If you have a valid reason, but just don't keep sending me things. All right. So what I was saying is, so we have 4 weeks left, right? Today we're going to wrap up Keras, and what's important about today is it's really good to put it into context, right? So the last homework assignment, you had 3 data sets, right? You had 3 data sets. What were the 3 data sets that you worked on for the last WECA sklearn homework assignment? Who can tell me? APS failure was one of them. That's correct. And also the Twitter, but not, like a Twitter data set that I gave you. And also, what was the other one?
It was credit card information, whether it's a false or good transaction.
Exactly. You had 3 data sets, right? You had 3 data sets. And basically, your homework assignment was to analyze it with WECA and then with sklearn and everything like that. Well, guess what? you're going to do that same homework assignment again, but this time you're going to do it with, as you might imagine, with Keras. Okay, so that's really, this will be, by the way, your last homework assignment. Okay, so I'm not going to give you a homework assignment on reinforcement learning. We're going to go over the code, and I'll show you guys everything that I've been up to with regards to that. You'll see it's a very amazing thing. And I'll go over unsupervised. You know, if you look, unsupervised will be the very last week before presentation. So I'm not going to give you assignments for these two, but I will give you obviously code, and we're going to go work through them in class. But however, your last homework assignment will be assigned today, and I'll put it up on the assignment link on Brightspace, but really what it is basically the last homework assignment, right? So you're going to take the same 3 data sets, which you have already hopefully know how to process, right? Because you did it for sklearn already. But this time around, you're going to analyze these 3 data set with Keras, okay? And I think that will complete your toolbox, right? Because your toolbox of machine learning now will have in it Weka, sklearn, Keras, which is TensorFlow for big data, and and so you'll be able to do a lot of things. So you'll do those 3 data sets, and the other data set that I'm going to add in there is MNIST. So actually you're going to do 4 data sets. But basically the idea is that today we're going to go over, we're going to do an example of a problem called the Xor problem. So Xor is just like the Xor operation in the Boolean tables, right? You know, you have the and, or, so this is the Xor operation that that you perform. We saw some of that in 350, for instance. So we're basically going to look at that problem. So as it turns out, that's a hard problem to solve, although it seems very simple. And so neural networks are good for that. And in particular, we are going to look at how to implement it with Keras. Okay, so just be aware. So your homework assignment, this last homework assignment will be to analyze the 3 data sets from before plus MNIST, so 4 data sets total, using the Keras API of TensorFlow 2. All right, so we will do a couple of examples of that today, but and really it'll be up to you guys then. You know, what I'm going to ask you is to try different architectures, right? So you're going to try different architectures and so on. Additionally, there is your term project, right? So the term project, those are due the week of December 7th and December 9th. Have we talked about the projects yet, guys? Have you guys formed your groups and everything?
Yes.
Yes, we have, right? Okay. And you've started talking, doing things with the topics, right? So what I'm going to do right now is I'm going to let me get through the Keras first. Okay, let me get through Keras first. And then after I get through Keras, remind me, please, I think we should have time. I want to give at least 30 minutes, and I'm going to create breakout rooms with every group. And I just want to see what topic you're working on, so I get a feel for whatever, everything that's going on. Okay. So remind me during the last 30 minutes of class today, we're going to do that. All right. So now then, so that we can get through the Keras examples, let's go ahead and switch over to the Scholar. Okay, so I'm going to go into Scholar. All right, just give me a second here. All right, so you should be seeing my Scholar over here. So if you remember, we had in desktop, I have 520, and I was working through TF basics. Okay, and then here is, so we've gone through these, and now today I'm gonna go through this one. So you should be seeing a folder called TF2 Basics Keras, right? And there are two scripts in there, the Keras MLP and the Xor TF2 Keras. All right, so these are the two examples that I'm gonna cover today. And basically what I want you to do is you're gonna do your homework based on these, okay? So we're gonna talk about how to create architectures. It's, you know, it's supposed to be easy to do it this way. I think it's debatable, but supposedly. So all right, so I'm going to take, you know, we're gonna take these two scripts. We're gonna start with Xor and just, you know, exactly what I did the last time around. We're just gonna go through the code. I'll explain it and then they'll run. Basically, they're not very long, so I think it should be pretty straightforward to get through these today. All right, if you have any questions, please stop me at any time. Remember, you can find those scripts on my GitHub as usual. And so just download. I haven't made any changes, so it should be the same ones. All right, so I'm just gonna open up Bash here, and you should be seeing, I believe, should be seeing the terminal now. All right, so then, all right, I'm gonna navigate to the desktop. All right, and then here, navigate into ITS 520. Right, so now, so we need to look at TF2 basics. Okay, and then we're gonna go into Keras. And remember, with these things, you know, the only way to really understand these scripts is to practice, right? So I've noticed some students that they just said, you know what, I just wrote everything from scratch so that I could see it. I do recommend you do that. Type these up on your own, you know, make your own version. All right, so I'm gonna go ahead and open the Xor script. So you can see this is the one. You can see it's not very long, actually. I'm gonna, you know, if you look, I'm gonna go over here and first of all show you everything, and that's it. So the code is actually quite short, and what I'm gonna do first, I'm gonna give you a quick overview of everything, okay? So as I said, this is called the Xor problem, and you will see in a second what that means. It's basically like saying instead of MNIST or instead of IRIS, we're using the Xor data set, right? But the Xor data set is actually straightforward, so we can create it from scratch, and you'll see that. And I actually like this script. I like this script more than the other one, the second one, because this takes the data, you know, data that you're generating on your own. So what I'm not going to show you is how to take data from those CSV files, for instance. So I was thinking, actually, you would be very well served if you did 5 data sets instead of 4. So I was thinking that you can do the 3 from before, which should be pretty straightforward, the MNIST data set, and actually the 5th data set is going to be those images. that I gave you, the fruit. Okay, you can download, more images. You can download other images because I actually only gave you 10 images there. But I'm going to ask you then, what I'm going to do is I'm going to give you until the end of the semester to complete this homework assignment. So that's a lot of time. And really, we're going to do 5 data sets because, as I've said many times in this class, at the end of the day, you write the script once, right? So you write the algorithm once, and then you modify it, sure. But the architecture and everything like that. But really, the thing that changes all the time is the data set. And that's why I stress that so much in 520, right? So if you notice, it hasn't been so much about the architectures. Everything has been pretty much a little black box. It's only here that right now, for instance, when we're going to do this example with Keras, we're going to look at a multi-layer perceptron. We're going to look at just a logistic regression, And what that means is how many hidden layers do we have between the input and the output layers, which I've explained already several times. Okay, so actually remember what I'm saying now. I'm extending the deadline of the homework, but really it makes sense that you should do 5 data sets. One that is pure images, as the fruit, apples, and bananas was. Make sure you have 200 samples of each. Download a data set online. MNIST, which I'll show you a trick to get MNIST really quickly, and then the other 3 CSV files. So right there, you have a lot of variety, okay? And every architecture will have to be different depending on the data set that you have. So those are the things that I'll be looking for. What we might do with that homework also is, since it's your last homework, instead of having you start it and then just submit a report at the end, what I'm going to do is I'm going to ask you to do it in about 2 weeks, do a demo of where you are so I can give you feedback, and then you submit the final report. So I want to make sure this is clear in your mind. Sometimes a lot of repetition is good, and this is important. All right, so are there any questions before I get started with this code about the homework or anything like that? No questions? You can all hear me, correct? I don't sound like a robot or anything.
We can hear you.
Okay, all right, thank you. So let's take a look at this one. So Xor, it's similar to the Keras idea. Obviously, a lot more power. This is TensorFlow. So not low-level API. Next week, when we look at reinforcement learning, we'll see the low-level API. It's really what I like. I just love the way that was created. And so I'll go over that as it relates to reinforcement learning. But so today, let's look at this one. So let's get started. So the Xor problem, in TensorFlow 2, the Keras API. I still don't remember the name of the person that came up with Keras. I really want to give him credit, but I just can't remember right now. All right, so import TensorFlow as TF, import NumPy as NP, and matplotlib, right? So we've already used matplot last week. Remember, unfortunately, there is no time in this class to teach you matplotlib. However, I want to, again, remind you that we are teaching a class next semester called ITS 265, where the class will cover, among other things, a little bit of linear algebra, a little bit of optimization, all applied mathematics for machine learning, and then it'll cover, of course, NumPy, matplotlib, and pandas, which is another one that there's no time for in this course. All right, so once we look at these 3, you have these 3 libraries, then we can go over here. In TensorFlow, you have and in NumPy, you have opportunities to set a seed value. It's just you don't have to do it. There's a default value, but you can do this sometimes. This is just here to remind you that you can do it. And this is because, a lot of the time we're generating random data, right? So you can see here, X and Y are actually going to be random data, okay? So here's the data set. Notice that I am not reading data from CSV files. However, in your sklearn code, you have already learned how to do that. All right, and you have learned how to slice the data, convert it into NumPy arrays, and plug it into these variables, right? So basically what you learn in sklearn, you will apply here for this problem. However, I am not in this example, you know, reading from CSVs. Instead, I'm just creating the data set. All right, so as you might imagine, we need to have an X and a Y, right? So you know those, that's, by now this should be very clear. X is the data, the features, samples and columns of features, and Y are the labels, one per row in your X, okay? So, so you have then, you know, the X data set and the Y data set, right? So we're going to initialize X to be numpy.random.uniform, right? So we're going to initialize our data set to be, you know, we use the library numpy, random data of a uniform distribution with a low value of -1 and a high value of 1. Okay, so this will be the data. We define the size to be just 200 samples and 2 features. All right, so everything in that data set of 200 by 2 will be a random uniform distribution with a low of -1 and a high of 1. So that means we're going to have 200 samples and 2 features, okay? And then from there, we're going to create the Y, which is also going to, we're also going to use, give me a second, guys. Sorry, guys, just give me a second. The problems of working from home. Give me a second. All right, sorry about that. So where was I? So we were looking at the code, okay? And so I have, you know, the X and the Y. Y are the labels, as you might imagine. So we use the NumPy module. And if you notice, we're going to initialize everything to ones, all right? And we just need to define the dimension, which will be of length X, all right? So length X is going to be the number of samples in this case. So we have 200 samples here, and that means this is also going to be 200 samples. So now let's go ahead and comment these out. And let's hope that this works. Right, so we're, you know, I'm just going to take the same approach as before. All right, so I added the comments. All right, so now let's see if this runs first of all. So I'm Control X, Y, enter. Okay. All right, so first thing it says, no module name TensorFlow. That's probably because I'm not in the environment, right? So on the environment list. Conda activate TF GPU. Okay. All right, so now I'm going to repeat the same process. Okay, it's taking a while there. All right, so that's good, right? So that means it printed out done, so the code worked. Okay, so now let's go back to it and get a feel for it. So I've got my X and Y, so I obviously want to, look at them. So let's look. So let's try to do print X first. Okay, so I'm going to do print X. All right, Control X, Y. I'm going to run this again. All right, and there's my data set. As you can see, it should have about 200 samples, and that's what the data looks like. Okay. All right. So now we need to set up labels. So we're going to have a two-class problem that's going to be either zeros or ones, basically. Right. So we're gonna change those values, and so I'm going to go back to the code here. Okay, and currently, it doesn't even make sense to print the Y's because I know they're all ones, right? So I know they're all going to be ones. So now I'm going to go ahead here and look at the next line, right? So in the next line, I'm going to convert some of the ones into zeros. So basically what's going to happen is, the rule is, for XOR, indices that meet the XOR condition, that is, that the column 0 for every row multiplied by the column 1 for every row, if that multiplication is less than 0, then that should be a 0, okay? Else, it should be a 1. So that's really the condition, and that's based on that condition, that's how we're going to set up our data set, right? So some will be zeros, some will be ones. The ones that meet the condition of, the 0 column times column 1 for that row, if that multiplication is less than 0, then we assign a 0. Right? You can see that there. So that's indicated by indices that meet XOR condition. Remember, this is slicing, so this is something that should be familiar to you. Whenever we do this, colon, that means that we want all rows, right? So this is a vector of size 200 and just of the values in column 0. Over here, this is a vector of all samples, but of all samples in column 1. So basically, the result of that is also a vector of size 200 of one column, which is the multiplication of all of those. So each multiplication is in one cell of the 200 in size column vector. All right, so now we can go ahead and print XOR indices for class 0. All right, and so that's going to be then, now all we have to do is, if you notice, we can do this little trick, and this is an advanced trick in slicing, which basically means that now we grab the entire Y vector, and we're going to assign a 0 to all the indices that meet this condition. Because when we do this, basically what's going to happen is that this is going to return a list. So it's literally like we're plugging in a list within this space, and it's a list of indices. Which indices? It's going to be the ones, where that condition is met, right? That is less than 0. Any, for all rows, any row where column 0 times column 1 less than 0, okay, put that index there, and then that index gets a 0. All the other ones stay with a 1. So now we can go ahead and print the y. And so we can see that effect here. So I'm going to go ahead, click Control X, Y, Enter. I'm going to do clear. And when I run it, hopefully it'll work. Right, do you guys see that? Now we have some zeros and some ones in that data set. So basically, you know, I created a little matrix 200 by 2 of the data, the features, and that's the X, and then also a vector of size 200 of size 200 by 1, which is the labels. Now I have arrived at my X and my Y. And from here, I'm ready to perform Keras. Keep in mind that for your homework assignment you have 5 different data sets. One is MNIST. One is images from a folder that are RGB, like apples and bananas. And then you have the 3 CSVs. The main focus of that is getting all that data to have the shape of these X's and Y's, right? To have the shape of these X's and Y's. And then, use it basically. So a lot of the work that I'm leaving for you, but you already had sklearn, so you should have an idea. And I showed you an example of how to do that with the images. And I will today show you an example of how to do that with Iris, how to read the Iris data as well. All right, so are there any questions at this time? Guys, are there any questions? Everything make sense so far? Yeah? All right, so it seems like there's no questions. So the next step then is, obviously, we want to divide our X and Y into train and test. Notice here it's called train and valid, like validation. It doesn't really matter. You can call this test if that is more intuitive to you. So let's go ahead and move the comment a little bit further down. So I'm going to move it down here. All right, so what are we doing? Very simple again, just some more slicing. Hopefully by now you've appreciated how slicing helps you. For the train, we're just gonna, so we have 200 samples. So basically we're gonna use 200 samples for train, 200 samples for test. So if you look over here, X is going to be, remember when we do, there's a comma, right? So the comma, so this is rows and then this is columns. So we're gonna say, when we do nothing colon 100, it means from the beginning to 100. So the first 100 samples, we want all columns, which is the 2 features. And then for the labels, we just say from beginning all the way to 100, right? So that gives us our train. So that's slicing, nothing surprising there, hopefully. And then the test or validation is going to be from 100 colon to the end of the data set. So that'd be 100 to 200, all columns, which is the 2 features. And then over here, it's going to be from 100 to the end again, and that's just for the labels. So with just this little trick, we now have our train and test data ready to go. Okay? So again, nothing too complex, as you can see. And then after that, the next step is, as I said, I'm not really doing explaining the plotting. Unfortunately, don't have time, but strongly recommend take 265 if you can. All right, so here, the same idea, create a plot, a figure. I already installed matplotlib from last week, so hopefully it's still there. And then you can see, we're gonna basically plot those data sets and we're gonna take a look at them, okay? So I'm gonna remove the comment. I'm going to leave, whenever I give you code for figures, I'm gonna leave it for you to figure out. All right, so I'm going to just add the comment here, and now hopefully we should get some really nice graphs. All right, so that's one of the beautiful things about matplotlib is the visualization of it. So let's go ahead and run the code, and we're gonna plot our data. And there it is. Look at how nice it looks. All right, that's our data. What do you guys think? Pretty, right? So we got, what do we have? We have all the samples. Remember, it's got X1 and X2, two features, right? And you know, the ones are, let's say, blue, and then the little triangles, the orange, is that orange or yellow, are the other class. So if you're building a machine learning algorithm, let's say that we're going to use logistic regression, which is a linear classifier, which basically means that we can only implement a line. Is there a line function, straight line, that can perfectly separate those two classes in this data set?
I don't think so.
You don't think so? Why not?
Because all the data is mixed up, like a triangles and the blue circles,
Yes.
they are more like a together in between.
That's
So if
right.
you
There is no line that can separate these with 100% accuracy, right? There is, unfortunately, I don't think I can write on here, but there is nothing like that, unfortunately, right? So there's no, you know, like straight line like that or straight line like that. So in fact, it seems like you would need like an 8, right? You know, or zeros or curves or something. Do you guys see that? Guys? And that's where neural networks come in. That's what I want you to understand. Linear classifiers, which are were always preferable in the past because they're easier. They didn't require as many parameters. You know, you would want a straight line. But then people like Marvin Minsky and people like that argued for many decades that, okay, you say that your solution is, your machine learning is so great and whatever, solve XOR. Where XOR was this simple data set and they couldn't, right? But then neural networks have proven, hopefully, that it is now more doable, okay? And that's what we're gonna see today. So this is our data set, okay? And this motivates the problem that we are trying to solve. Make sense? So there is, although I can't draw here, there is no straight line. All right, so I'm gonna hit on the close here, let it finish up. All right, so I'm gonna do clear now. And now we can go back to our code, right? We can go back to our code. All right, so I've done, we've got our X train, Y train. Notice that we plotted the data here. Just quickly, you know, these are the X's, and then, you know, notice if a Y was 0, if the label was 0, then we got those indices. If the Y was 1, then we got those indices. And then we just specified the color and shape and so on. So that's how we were able to plot our data over here, right? It's actually not that hard, just, you know, play with this. All right, now you might say, well, that's great and all, but I want to do some, you know, machine learning. So now we're going to do that. I'm going to move these little comments out of the way. And now we're going to move over to logistic regression. Remember, you've already seen that name a couple of times in your, homeworks, right? In sklearn and Weka. Now we look at logistic regression. Now we're not going to get, remember, so much into the architectures and how, or the math. That's more of a 5:30 topic, but I did do a video on these, right? Remember that video where I showed you, this is what a neural network looks like for logistic regression. This is what a neural network looks like for, this is what a network looks like for logistic regression. This is what a network looks like for neural networks. This is what a network looks like for deep neural networks, right? With multiple layers, remember. So it's difficult for me because we're doing this online, you know, to stress. When you get confused about this, go back to that video in particular. All right, so logistic regression, as I said, is the architecture that has no hidden layers, okay? No hidden layers. So logistic regression is a linear classifier, right? So I'm actually going to go ahead and switch over to the whiteboard. All right, there's the whiteboard. You should be seeing that, I believe. So logistic regression. How many inputs do we have in our data set? Right, that's our data set, correct? So how many? So if I draw the architecture, it's a logistic regression. Logistic regression has no hidden layers. How many inputs do I have? 2. Why? F1, F2. You should know this by now. Okay, these are exam type questions. Then over here, sometimes we can have, when we have a 2-class problem, we can have 2 neurons. The way that Keras does it is actually they only use 1 for this type of problem. And because this is the XOR, actually, it's kind of a, you know, if you've ever looked at like digital logic, you know, logic gates, so it's sort of the same idea. Logic gate, you know, sort of looks like that, right? And so we have, you know, 2 inputs and an output. So it kind of falls in line with that idea. So anyway, this is our network. W1, W2, X1, X2, Y1, plus the bias, which would go over here. And so that's really what the network looks like. This is the architecture of logistic regression, okay? Of logistic regression. So that's what we're going to take a look at right now. So I'm going to go ahead and switch over to the code again. And now that you have an idea of what I'm talking about, we can write it out in Keras. All right, so that's our goal now, is we're going to write it out in the Keras very high level. This is very high level API, I should say. Keras has the functional API, which is a little bit lower level, I should say. But this is the Keras very high level API. And it actually, there's a lot of ways, guys, to write things in Keras. So this is just one. Later on, we're going to see another one in the other example. All right, so we're doing good on time, I believe. So now, I've plotted the graph, and now I'm going to go ahead and define over here my logistic regression algorithm, which I've already talked about a little bit. No hidden layers. Notice that comment there. So I already drew the architecture, and you can see over here that pretty much what I drew is I've written here, 2, 1. That means there's 2 neurons in the input, 1 neuron in the output, and there's going to be a bias of 1, right? So those are the parameters that I drew before. And now here comes the magic, right? The magic of Keras. We're going to build the network architecture. Usually you create a variable. I've noticed they call it model, but you can call it whatever you want. You can call it model logistic regression. I would actually suggest that, but it's up to you how you do it. You'll develop your own style. So model, and then you assign to it tf.keras.sequential, all right? And that's it. When you do that, you're basically saying, okay, now I'm about to lay out the architecture of my model. And there's, as I said, multiple ways of doing this. The functional API allows this to be a little bit more intuitive. This one is a very condensed way of doing it, which is fine, I guess. All right, if you notice, I think I've said this many times, I like to write this type of code because TensorFlow is so verbose that I like to write it as a jQuery style. Okay, so if you notice here now, I call the model and I do .add, open parentheses over here, close parentheses over here. Then within this parentheses, you can define as many layers as you want, separated by comma. Here, I just have one because this is such a simple architecture. So I'm just going to say I want one layer, one dense layer called tf.keras.layers dense. Remember, dense just means fully connected. That is to say that every neuron from one layer is connected to every other neuron of the other layer, okay? So once I do this, you can see here, I set, first of all, the units. Usually it's the units in the output layer. So it's always like, you're always defining of the two layers, the output one, okay? So you do units equal 1 because there's only one, the output. So just one neuron in the output layer, you can see that. That's why it's 2 by 1. The input shape, this is only defined usually in the first layer, okay? And here the input shape is 2. Notice that in TensorFlow, everything is a tuple when you define these shapes, even when it's only like a vector. This is the format. But it's 2. That's x1 and x2, right? Or f1 and f2 from the 200 by 2 x data set, okay? And then the activation function here, it's going to be sigmoid. Remember that these functions are the mapping functions that allow you to take a real value number and mapping it to a value in a range between 0 and 1 in this case, which kind of mimics, in a sense, like a probability. You know, what's the probability it's going to rain today? I don't know, 60%, you know, so that kind of thing, 0.6. And that's it. Look at how simple and elegant that was, right? So, yeah, Keras is okay. All right, so then we do this, and now Keras has this idea of printing out model.summary. What's helpful about this is that it sometimes tells you how many parameters you're going to calculate. Remember, parameters just means all the weights, all the biases that the machine computer needs to figure out. The more you have, the more powerful computer you need. Hence, that's why we're using the Scholar, GPU Scholar. All right, so let's go ahead. So at this point, remember, you know, I've said many times, usually what you do in Python is you're creating the computational graph, but then it needs to be compiled and become C code and all that efficiency. And you can see that that's sort of being done here. But for now, notice I put the comment here. So we're just going to print the summary, okay? We're just going to print the summary. I'm going to go ahead and run this one. It's printing the data there, and then now they're called a little what you call it, TensorFlow. Notice we're not using GPU, we're only using CPU here, and you can see the model highlighted there, right? So it's sequential. You know, there's only one layer. None just means that it's the number of samples, right? And then the output is 1, and then the parameters are 3. Okay, which makes sense because it's going to be W1, W2, and the bias, right? So there's 3 parameters for this very simple model. But as you start adding layers and so on, it just becomes, you know, huge. Are there any questions so far, guys? No questions? Everything making sense? This is very important. Remember that this is the essence of your homework assignment. I'm going to ask you for the 5 data sets, you know, I want you to do a logistic regression. I just showed you how to do that, but then I want you to do a neural net and a deep neural net, right? You know, remember, this class is not about deep neural networks, but this is it. This is where finally I'm teaching you how to do a deep neural network, what that is, right? You know, the 530 class really does lay the foundation of what a deep neural network is and everything. But here, you know, just we're kind of finishing up at that threshold. All right, so I'm not hearing any questions. And unfortunately, I can't see your faces, so I don't know your expressions, but please stop me if you have any questions. All right, so now we keep going, right? And so you might say, all right, what's next? I've got the summary, right? But what else do I need to do? Well, as it turns out, I've already talked about this, right? So when I talked about machine learning, if you don't understand the theory yet, just sort of memorize this. Remember, I've said machine learning, there's two equations. What are the equations? One is called the inference function, which is that y equal mx plus b. And the other one is what? The optimization, which I gave you the example of linear regression, right? Which is, you know, y minus y hat squared, and you minimize the sum of those, which is LSE, or the sum of squared errors. However, remember that that only applies to linear regression, and the name of that for classification is called cross entropy. Okay, cross entropy. So we need to have that parameter. We also need to know how we're going to learn the weights. So that's the giant walking on the mountains, right? Remember, that was called gradient descent. Okay, so that's the other algorithm that we use. Beyond that, the whole back propagation, feed forward, all that, that's something that's done behind the scenes for you via TensorFlow. So you don't have to worry about that. You know, the back propagation algorithm, you know, if you take 365, which is a course that we're also offering starting next semester, that course will be more about those fundamentals like, you know, back propagation and how to write KNN from scratch and so on. But in this, you know, because you know, it's a 300 level class, so it sort of makes sense to do it there. But anyway, in this class, we're not covering that. You don't have to worry about it because, as I said, TensorFlow does that for you. However, you do have to worry about those few things that I said: the inference function, the optimization function, the optimizer that you're going to use, and also the metrics. Remember the metrics like precision, recall, F measure, and all of that? Well, we still do that. So the way that you do that in Keras now is that you're going to call the model again, and then you're going to say compile, and then you specify the parameters. So it's actually pretty straightforward. So for the optimizer, what do we want? We're going to use tf.keras.optimizer.sgd. This stands for the stochastic gradient descent algorithm. All right, and this is basically stochastic gradient descent is basically the standard. There's also another one called Atom, the Atom optimizer, but it's still a gradient descent. It's just an optimal one. Keep in mind this SGD, you know, believe it or not, all of machine learning relies on this, on the shoulders of this one thing, and there's only one. So it's impressive. So anyway, that's kind of just usually just leave it as that. The loss function, remember that whereas the inference function is this one, this is the inference function, right? Y equal mx plus b, it's this one. The loss function, which is the y minus y hat squared, you know, all that. In the case of classification is cross entropy. So notice that all we have to do is call it by saying tf.keras.losses.binary cross entropy. And that's it. You don't even have to worry about it. And then finally, the metrics, if you notice, you can actually provide us a whole bunch of metrics that you want, like F measure, precision, recall. Please, when you do your homework assignment, you will need to add those in here, okay? So don't just do it. So notice here, I've only provided an example, tf.keras.metrics.binary accuracy, but you will have to do the other ones. Also, very important, notice here, binary cross entropy. There are two types of cross entropy: multi-class cross entropy and binary. Binary is when you have two classes, like let's say, like we have here, you know, zeros or ones. When do you use multi-class entropy? What's an example of that? Well, Iris has 3 classes. MNIST has 10. I don't remember the fraud and car failures and the Twitter one. I'm not sure how many classes they had. I can't remember, but you will have to change that accordingly. All right. Any questions so far about anything that I just said? No? Can you guys hear me though?
Yes, we can.
All right, great. All right, so it seems like you're understanding. That's what I'm assuming, since I've heard no questions. Okay, so once you define those parameters, obviously comes the training. All right, this is the training over here. So notice, you know, I usually like when you do the training with a for loop, but that's not something. But that's something. Let me say it this way. That's something that can be abstracted in the high-level Keras API. Right, so instead of doing a for loop and reading the data like that, I just find it more intuitive. You can do it this way. So usually you create this history variable, and that just will hold everything, all the data that you might want to plot and print out. And then you do model, the same model as before, dot fit. Remember, that's just a variable name that you chose for the object. And then you specify the parameters. So you're going to give it the X train and the Y train. Right, makes sense to train it. You're going to give it for the validation, you're going to give it as a tuple. Notice that you have to put it in a tuple, X valid, Y valid, or X test, Y test, depending on how you called it. The number of epochs that you want to run in your training, that's going to be 200 in this case. It could be 400. That's just the number. Imagine the number of times that you're going to train. So this is a trick. This is something that to me was took me a while to understand, that in machine learning, you give a model all the training data more than once, right? So I would have thought if I have 100,000 samples, I'm just gonna give it all the data once. And I thought, well, let's say I run an epoch and I give it all the data, and then I start again and I give it all the data again, and then again. I thought it was some kind of a cheating type of a thing. I must be cheating, but it actually makes sense to do that because it reinforces to the algorithm certain things. Also, the fact that you're initializing the parameters every epoch by random helps out the model to look at things a little bit differently. So you get the data, but this time, you know, you're in another place with different set of weights, so you might learn something different. So in essence, basically, you give the data more than once to your model. And that's a standard approach, and it works. The batch size that you're going to give is going to be batches of 2, which basically means that you're going to grab the data, you're going to do 200 epochs, and then you're going to slice the data out of that 200 in batches of 2. And that's how you're going to feed it. The batch size is important. Here, it's a little less relevant. Just use, you know, some standard batch number. But as you know, once you get into more complex problems, it does make sense. Like there are some problems where the data or the model is so big that you can't give it more than, let's say, 64 samples per batch. Otherwise, you run out of RAM memory. Things like that. Or GPU memory, actually. You can actually exhaust the GPU's memory as well. All right, so, and then verbose, you know, as that implies, it just prints out more data as it's fitting the model. All right, so now that we've fitted the model here, that means we've trained it, right? We're training it, we're fitting the model. So now let's go ahead and run this one. All right, so I'm gonna run this one, Control X, Y. Okay, my little data set is there. And then it did the summary. You can see that that's the summary. And now it's doing the fitting, which basically means it's doing the training, right? So let's give it a second there. And it basically fit the data. Okay, so now it is trained. Let's go ahead and, you know, I strongly suggest that whenever you do this, you know, like some students, I noticed in their homework, they said, I like typing all this. go ahead and do it. You know, change parameters just out of curiosity. What happens if I do a 1 there? For instance, right? What happens if you do that? Run it again. Take rid of that. And you can see that I changed the verbose to true. And what is this giving you? It's giving you, for every iteration, you know, that whether you're feeding the data in batches, it's showing you how the loss function is changing, right? Usually you want to minimize that loss value. So you want it to go down, or the accuracy also, you can, excuse me, you can see it here, right? So notice the accuracy. What do you notice about the accuracy in these three? What do you notice, guys? For a 2-class problem, right? So if I asked you on the exam, it's a 2-class problem, XOR. Do you think this classifier does well, or do you think it does badly? Or does it do, you know, somewhere in between? What would you say? Nobody? So it's got an accuracy of 65. So a value of 65 is not great, right? So for the XOR problem, that's what Marvin Minsky was saying, right? Linear classifiers don't do very well on this. Oh, you know, uh-oh. All right, so anyway, we've seen this, so hopefully that made sense. And here we just see the accuracy on the validation. We see it on the, you know, on the train and the test set, basically. So really, I guess you would want to look at it here. It's about 71. Okay, that's the best that my model can do, it seems. All right, but we probably want to consider, can we do better? So let's go ahead now and go back to our code, right? So we're going to go back to our code, go back over here. And now we're going to want to visualize a few things. Here again, guys, with visualization, I'm going to leave this for you guys to play around with these. As I said, you know, we're short on time. But I will run this code, which will provide us some insight into what's going on in our model. So I'm going to remove these comments here. I'm going to need to install, if you can see here, install this library for visualization. On the Conda Linux environment, I'm going to have to type conda install mlxten -c conda forge. So I'm just going to, you only have to do this once, okay? I'm just going to copy it. Right, and then you can see here I'm doing the library, calling the library. I'm calling the history, hist.history. So notice that's this history over here. So basically the results of fitting my model, okay? The results of fitting my model. And then I'm gonna, you know, you can see here, I'm gonna plot all that, I'm gonna do a lot of matplot magic so I can plot things. So the first thing is, let's install the library, okay? So I'm gonna go ahead here, run that command, conda install mlxten -c conda forge. So go ahead and run that command as well on your Scholar or your conda environment. All right, and hopefully it'll work. All right, so just hit yes over here. Let it install. All right, so it's doing its thing. All right, so we've got our code ready. So now let's go back. Go back. So we're just going to plot it, right? We're going to plot this data, and this is going to reflect the results that we have in our history, right? So you can see it's going to look very impressive if it runs. So I'm going to run this now. There we go. All right, there's my data over here. I left it verbose for the training. 70. Oh, look at the accuracy is improving, right? You saw 50s, 60s, 70s, right? So it's improving, but now we're going to plot these results as well. That's our intention anyway. What happened there? Oh, there we go. All right, so it didn't crash. That's good. So here we have our results. So now when you guys write your papers, your research papers, you do your thesis and so on, you can use these tools to, show your results, right? All right, so here we can see the loss functions for, remember, in machine learning, you have two functions, inference and loss, right? So the loss is this one here, the cross entropy. Notice that the loss is really high for both train and validation. And then over time, it starts to improve, right? They both start to improve. Here, this is the accuracy of the model that, it went up to like 70%. It's reflected there with the little 70 over here, right? We plot both for train and validation, and we can see both of the results very nicely. And then guess what? Remember, we had looked at our data, the little triangles. Notice of all the classifiers possible, which is basically a straight line in this two-dimensional space, this is the most optimal one that the model was able to find. But as you can see, there's a lot of misclassification because these are blue, obviously, but there's some blue over here. And then these are supposed to be the triangles, orange. I think this looks orange to me. But there's a few misclassifications here. That's why this accounts for about 70% of your accuracy. Does this make sense, guys? All right, are there any questions? Please stop me if you have any questions, but hopefully this should be pretty intuitive. We saw the loss function, we saw the accuracy over here, and we are seeing the linear classifier because we're only using logistic regression, remember. All right, so now let's go ahead. I can go ahead and close this one over here. All right, and it closed successfully. So now I'm going to clear the screen, and I'm going to go back to my code. So I'm going to go back, nano, scroll all the way down, and we were able to print the data, and here it is. Looks pretty good. All right, so now, guess what? Now we're going to think about the problem a little bit differently. So I'm going to go down here, and I'm going to do the same. I'm going to put the comment about summary here. All right. So now let's look at this one. We said that the problem initially was that we only had an input layer and an output layer and no hidden layers, no activation functions. Without that, we were not able to create nonlinear separation boundaries. We only had access to a straight line. So we're going to take it up a notch. And now I'm going to say, you know what? I'm going to change my architecture, which basically means my inference function, and now add hidden layers to create nonlinear decision boundaries. And we should be able to see that when we plot our little graph in a second. So now again, same thing, you can set a random value over here for the parameters, but really we're going to set a new model. You can call this model underscore DNN, for instance, or two hidden layers, something like that. tf.keras sequential again. And now we're going to set up the architecture. Notice that here we take a slightly different approach to the architecture. right? We're going to say, you know, we use model.add to sequentially add the layers, okay? To sequentially add the layers. So for instance, this is something that I want you guys to play with when you do your homework assignment. So here I have tf.keras.layers. Dense, remember, is a fully connected. The first layer is going to be of 4 neurons. Here, because it's the first layer, you can define the input shape, which is going to be 2, because we know there's 2 features in our data set, right? There's, you know, in our data set of 200 by 2. So it's 2. And then the activation function, we know that, you know, remember, these are the mapping functions that take values from any number and map them into ranges from -1 to 1, or ranges from 0 to 1, or in the case of ReLU, from 0 to whatever the value is. So this is usually referred to as the hockey stick, has a shape of a hockey stick. All right, so create the first layer. It's equivalent in terms of weights and bias to 2, 4 bias 4, okay? Because there are 2 inputs and the layer has 4 neurons. The next layer is going to be tf.keras.layers.dense, also fully connected, also size 4, also activation ReLU. So the size of this is now 4 by 4, because this 4 is the previous 4. So the inputs from that, the outputs from that layer become the inputs to this layer. And then my new layer has 4. So the layer, those 4 new neurons also have to have 4 biases. And then and I'll draw this in a second. And then this one is the TF Keras dense again, another 4. You can play with these values. Okay, there's no science to these. It's more of an art. So play with them, see experimentally, look at your results. Activation is once again ReLU. Again, 4 by 4, because the output neurons of this layer become the inputs to this one. We also want it to be 4, and because this is 4, then the bias is 4. And finally, the last one, the way you do it in Keras, you know, you can define just 1 neuron. TF Keras dense units equal 1, right? Because it's just a classification problem. Either I think it was -1 or 1, something like that. No, 0 and 1 for XOR. And then the activation does change from ReLU to sigmoid. You want to limit. ReLU has a range from, let's say that the value is 50, right? So then it's going to be from 0 to 50. If the value is -50, it's still from 0 to, you know, whatever the value is, but it doesn't allow negative, so it would be 0. But sigmoid maps something to a range between 0 and 1. So any value will be mapped to something between 0 and 1. All right, and then once we do that, we've defined our architecture, and guess what? You just created your first deep neural network. Congratulations, a very simple one, but you can see it here. Here's the model summary for the statistics. You know, basically we can see the parameters. Now let me draw this, okay? I'm gonna switch over to the whiteboard, and that will allow me to just show you the architecture. So I'm gonna go ahead and do this, and then go over here, all right? New slide. So this architecture looks like this. It's got 2 hidden layers, 1 output layer. I know this one's in 1, this one has 2, but these have 4. Okay, that's why this is 4. Oh, sorry, this is 2, 4. This one is 4, 4, and this one is 4, 1. Okay, and you know, like the weight matrices basically. And then the other thing that's important is the bias. Where does that bias come in? The bias is just once you have the value of these, you do plus B, plus B, plus B, plus B. You know, this has its own set of biases. This one has its own set of biases. And this one has its own set of biases. These are all different, okay? All right, but that should be it. That's the architecture that I just created. You know, I'm not gonna connect all of these, of course. That would take too long. But you can see they're all fully connected. And that's your neural network. So this is the input, the output, hidden 1, hidden 2. Okay? So now let's go back to our code. All right, and let me just confirm that I did that right. So yeah, so we have one input layer, 4. Oh wait, there's actually, did I miss one? There's one more, right? So there's 2 to 4, then 4, then 4. Oh, okay, so I'm missing 1 actually. Apologize there. So there's one more layer. There's actually 3 layers. And then the output layer. Okay. So there's 3 of them. I thought that looked squirrely. All right, so there we go. So that, I think that makes a little bit more sense. All right, so that's a deep neural network of 3 hidden layers. Okay, so we've created that, and we have our analysis here. So we have, hidden layer, hidden layer, hidden layer, the output layer. Notice that each layer has its activation function, ReLU, 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 and the signal. All right, and then now we can print out model.summary. So I'm going to hit Control X, Y. Excuse me, sorry. All right, this is data. Training. All right, the results. But now we're building the next architecture, and you can see here in the summary, notice that how it exploded in parameters to 57. Notice all the layers here, right, that we've created. Okay, so that's our model, right? So now let's go back into our code. Scroll all the way down. All right, so this is where we are. So now we repeat the same process as before. Same thing, we compile, optimizer, stochastic gradient descent, binary cross entropy, metrics just accuracy. Then we're going to fit the model, exactly what we did before. X train, Y train, validation is X valid, Y valid. 200 epochs, batch size of 2 verbose. All right, and I can run that code exactly as I did before. So it'll do the same thing. The only thing is, let me change this to verbose equal 1, so we can see now the accuracy remember, before we're doing it with logistic regression, a linear classifier. Now we're throwing all the power of deep neural networks into this. So let's see if that improves our results, okay? And also, we're going to plot the data once again, the exact same plot that I did before, doing it here. Okay, so basically that would be it for this problem. So let's go ahead and see how it performs. I feel like I'm missing something. I'm not. I'm just repeating what I did before. All right, so let's go ahead. Notice all I changed from the logistic regression was this. Okay, the architecture or the inference function. Let's see if that really does make a difference. All right, so now we're going to run it. There we go. There's my data. That's the problem. Training, notice the accuracy going up. 50, 60, 69, 70s, 71, 71-ish. there's the plot with logistic regression. You can see the accuracy plateaus around 70. We can only draw a linear classifier, right? Okay, now we're running the deep neural net. Let's look at the accuracy over here. 60, 67, 70, oh, whoa, 80, 90, 95, 96, 97. Look at how it jumped. So apparently deep neural networks do work, right? Look, it's in the 90s. 94 was the last one. Now let's look at the plots and let's see what we get. Aha. What do you guys notice? Look at the loss function, right? Compare this to the previous loss functions. Look at how it went down really low. Look at the accuracy. Before it had plateaued at 70, around here, right? Now look, we're at 100% almost. Look at how at epoch 50, it started to climb around 100 epochs, it stabilized at a very high score. And now look, the very valuable thing is, what's really great, and I want you to understand, is that whereas the linear logistic regression could only fit a line, now a neural net can create these shapes, right? It can create these shapes because it basically, think of it as it's approximating a whole bunch of hockey sticks or lines to create this shape, right? And if you notice, look, it was able to create this decision boundary and that decision boundary, which basically allowed it to contain in the blue all the blue squares and in the orange all the orange triangles. So basically now this model does really well, does better, certainly. And that's it. That for this problem, remember this is a binary problem. A lot of the data sets that you'll be working on are multi-class, so they'll be a little bit different, but that's part of the homework, right? That's part of the homework. All right, so this is a very good stopping point, actually. We're only like 3 minutes past. So we've completed Keras. That honestly completes Keras as far as we're gonna take it this semester. We're gonna take a 10-minute break. And then when I come back, I'm going to do a second example. I'm going to go through that other one just a little bit faster because it's very similar. And then after that, I want to talk to you guys about the project and the homework. And then, you know, that basically means we'll be done with supervised learning for this semester. The functional API, if I have the Keras functional API, if I have time, at the very end of the semester, I'll cover it, but just keep in mind that's something that if you take 530, you would see there. Functional API, as I said, is Keras, but at a lower level, gives you a little bit more power. All right, so although this, you know, hopefully this should be enough for you guys to do a lot of machine learning. So before I close out these graphs, or before we take a 10-minute break and I start creating this video, are there any questions about anything that I've said? No questions, really? Was all this that clear? Are you guys still there? Did you fall asleep? All right, no questions. All right, so it seems like it was, I'm gonna believe you, so no questions, all right? Okay, so then it is 3:25. Let's take a 10-minute break. We will start the second part of the class today at 3:35. Meanwhile, I'm gonna exit out of here and start creating this video, okay? All right, so I'll see you guys in 10 minutes.